Well, let me thank the organizers for the invitation to discuss here. So I'm going to talk about something quite similar to what Frank just talked about. And this is work that I did with Thomas Klein-Corning and Lloyd Kerview. Our approach is similar in nature, but we are focusing more on the states rather than the operator growth. But I think there are quite a lot of similar ideas that come in it, and my introduction has some overlaps with Frank's, which is good, so I can be a little bit quicker in the introduction. Well, the basic question that we are interested in and that we've heard a lot about in this conference is what happens in quantum quenches. Do you thermalize, or are there some other generic behaviors that you get under closed quantum many-body time evolution? So in principle, we set things up here. This is the setup. You prepare some initial state, which is not an eigenstate of the Hamiltonian, and then you time evolve for some time, and then you make some measurement at the end. And the most generic thing that we expect to happen is that after a long time, you just reach some thermal state. Well, of course, we know this is not what happens all the time, and one of the generic ways when this does not happen is many-body localization. And many-body localization is nicely analyzed in terms of entanglement. Actually, many of these dynamics are nicely analyzed in terms of entanglement. And you can basically look at it in two ways if you do a quench. Then the entanglement goes from increasing linearly in time in kind of the ergodic phase to logarithmically in time in the localized phase. And in between there's some region where we have slow growth or slower subdiffusive type of, or subballistic growth of the entanglement. One can also look at the eigenstates, and the eigenstates in the localized phase have a area law entanglement and a volume law entanglement in the ergodic phase. This is kind of the broad features just of the von Neumann entropy. It's just saying, okay, what is the total von Neumann entropy? Is it a log? Is it T? Or is it the volume law? Or is it an area law? And in some cases, it's nice to know a little bit more detailed structure of the entanglement than just whether it's a volume law or an area law. An example of that is if you look at the structure of the eigenstates, then at the transition or close to the transition, the detailed structure of the eigenstates reveals a lot about the mechanism, or could reveal a lot about the mechanism of the many-body localization transition. But I want to focus in this talk on the dynamics in this region here, namely where at long times you reach the thermal state, and we want to understand how to kind of push the time evolution to long times beyond times where matrix polar states work. Now, Frank mentioned this a little bit about why this is hard, and we also heard in Timo's talk about the entanglement barrier. So let me explain what this is. So if I just look at the entanglement, and just to define it, the entanglement entropy here is just the von Neumann entropy of a reduced density matrix of let's say half of the system. So rho A is the trace of A bar over the full density matrix, which is just obtained from the time evolved state in the usual way. Now, in a diffusive system, this entanglement entropy grows linearly in time. So if I want to characterize this state with a matrix product state, I have a bond dimension that grows as e to the entanglement. So this is exponentially in time. So this is what Frank talked about in the matrix product state, that we have a bond dimension that's growing very fast with time in these systems. So very quickly, exact matrix product state algorithms break down. But in the opposite limit here, if you're in a thermal state, especially at high temperature, these states are actually quite simple in a sense, and in particular in the following sense they are quite simple. If I imagine trying to purify my density matrix at infinite temperature, which is just an identity, this can be done in a very simple way by just adding auxiliary degrees of freedom, one for each physical degree of freedom, and entangling on every side the physical and auxiliary degrees of freedom. For example, you can put them in the singlet state, and then if you trace over the auxiliary degrees of freedom, you get back the thermal state. So this is a very simple state in this purified sense, because it's just a product state of these singlets. So it has very low entanglement. So basically, you expect that at in terms of these density matrices at long times, your states are quite simple. So we have this picture that we also saw in Frank's talk. That if I'm trying to do the pure state dynamics, then the entanglement entropy is growing very fast in time. While if I look at the entanglement between in a purified state, then that entanglement is going becoming very small at long times. So in the infinite case, it's basically 0 at long times, and if I imagine evolving back, then that entanglement grows. So somehow it's easy to represent states here, it's easy to represent states here, but in between it's extremely hard. So what we would like to have is a way of doing an evolution that is exact going through this barrier. I mean, it cannot be completely exact, but we would want it to be exact in that it captures the essential information in the thermal state. So how does one do that? And of course, many people that have looked at this question, I didn't put all the references, but they've heard a few talks already in this conference with the same kind of question. And Frank explained this brute force method, where you just say, okay, let me just conserve the energy and just go through it and hope the best. So I'm not going to say more about that. Okay, so it's good to think about a little bit what happens in the thermal part. How is it that it thermalizes? And this is described by the eigenstate thermalization hypothesis. And the key point here is that the full density matrix, of course, is pure at all times, which means that it's not the full state of the system that thermalizes. It cannot. It's a closed quantum system, and that time evolution is unitary. But instead, what thermalizes is expectation values for local observables. So if I look at the expectation value of local observable at long times, it becomes equivalent to the thermal density matrix of some local thermal state. I mean, another way to say this is that a reduced density matrix of A, where A is some local region, is essentially a thermal state. Okay. Now, if I look at the argument going into how we get this, basically we write down the time evolved expectation value, and if there are no degeneracies in the spectrum, then the off-diagonal terms will dephase, and you get this expression for the diagonal part. And the key assumption of ETH is that this expectation value of the diagonal terms only depends on the energy in a smooth way, and therefore if the initial state is somehow peaked in energy, I can take it out of the sum and I get the thermal state here. Okay, so one key thing that goes actually is kind of hidden in here is that the detailed entanglement structure of the eigenstate is actually not that important. What is important is that there is a flow of information from relevant to irrelevant degrees of freedom, and that leads to large entanglement, but that entanglement is basically there to act as a bath for local degrees of freedom. But how exactly that happens is not so important in this argument here. It is happening that it happens, but it's not so important how it happens. So there is an analogous thing that happens in classical mechanics. So I kind of like this analogy, so let me give it, but it should be thought of just as an analogy. So there, if I recall how to derive the Boltzmann equation and what goes into it. So if I want to describe the amount of information I have about some classical system with n degrees of freedom, let's say, I can characterize that by the Shannon entropy, which is just this integral over some probability distribution. And now I have to pick the probability distribution that I'm interested in. And if I pick the n-particle probability distribution, which knows the position and momentum of every single particle, I will get this entropy here, which is just the integral of rho log rho of this n-particle probability density. Now if I ask what is the time variation of this entropy here, I find that it's 0, and it's 0 because I am keeping track of all information about all particles at all times, and therefore there's no generation of entanglement of information entropy. If instead of using rho I use f, which is the one particle probability density, where I've just integrated out all but one particle, so I use this f in the Shannon entropy, I get the usual entropy function, and this entropy function in fact increases the time. But if I know f, I can also get essentially all observables of interest. For example, currents I can get by just integrating the momentum weighted by the one particle probability density. Okay, so I choose here to keep only track of local information because that's the information that I need in order to get simple observables. But suppose I want to know what is the time evolution of this f. I could of course, if I know the time evolution of the full state, I can get f by just integrating, but that will be an overkill. So I would like to know a time evolution equation for f itself, and that of course is the Boltzmann equation, which has this collision integral, which in general depends on two particle density function, because I need to know the probability that two particles come together and can scatter. So if I were to write the exact collision integral, I will need to then find the time evolution for f2. That in turn would depend on f3 and so on. But I can close this set of equations by finding some approximation for f2 at the point of the collision here, and that's this assumption of molecular chaos. So I approximate the exact collision integral that depends on f2 by some approximate collision integral that only depends on f, and that closes that set of equations, and I get a time evolution for f. So here I want to do something similar for the quantum information. So I want to first, so there are two parts. There's one part which is trying just to construct a way of keeping track of where information is flowing, quantum information is flowing in many-body dynamics. And for that, I'm going to introduce the information lattice, which is just a way of keeping track of where and on what scale information is in a given state. And with this information lattice, I can nicely visualize how information flows during generic dynamics. So that's the first part. But then the second part, which is this one can use for exact dynamics also. But the second part is then to try to use some insights from the flow of dynamics on this information lattice to construct some efficient algorithms for the time evolution of thermalizing systems. And beyond, it doesn't only have to be thermalizing. Okay, and what we are going to be interested in is just local observables, and therefore what we want to keep track of, what is the equivalent of the f in our case, is the reduced density matrix on all sets of some size L. So this is just all sets of size L centered on side N. And we call this the local information. That's the set of all reduced density matrices. If I know the set of all reduced density matrices, I can calculate all local observables that have a range which is smaller than L, smaller or equal than L. Now, of course, if I try to find the time evolution of this local information, it's some functional, at least for nearest neighbor Hamiltonians, of the local information on L+1 sides. So that's, again, kind of similar to what happened in the Boltzmann equation, where we got F2 on the right-hand side of the equation in the collision integral. The same thing is happening here. So the question is, can I find a way of approximating the right-hand side by some functional of only the local information on scale L? So that's the task that I want to kind of discuss. Now, there are, of course, examples where this doesn't work. For example, if you have some information that is global that at some point you want to bring back to a local information. Suppose, for example, if you have a bunch of non-abelian anyons and you're storing some information in these, and you're doing some braiding of these, then there's some information which is not stored locally that you cannot access through these things here. But other than that, we should be able to do this. Okay, so a couple of quantum information concepts that I need to build the information lattice. The von Neumann information is defined as this, just the log of the dimension of rho A minus the von Neumann entropy. And then there's the conditional mutual information, which is this particular combination of the mutual or the von Neumann information of the density matrix on the union of A and B, and the density matrix on A and B, and the intersection of A and B. And the interpretation of this thing is that it's the information that's in A and B, but not in either A or B. So the way I will use this is that these will be the smaller scales, this will be the larger scale. So this will tell me about the information that's on a larger scale that I cannot get on a smaller scale. And then what I want to do is I want to decompose the total information into these local information variables. And the way I do this is that if I have a single side, then I just define the information on a single side as being the information in the reduced density matrix of that particular side. Then I go to the next level. Then I put the point here in between, and I say that the information on scale 1 is the information that is in the union of the two below, that I cannot find separately in either this one or that one. So it's a conditional mutual information between these two. And so on. Once I go to scale L, then the information on side L is the information that I cannot get in either of the subsets, so that I cannot get on any smaller scale. Once I have this, it's possible to define information currents, which are just coming from conservation of the total information. And the total information is conserved because we have a closed quantum system. And I can, through this identification of local information here, I can define this continuity equation. And for nearest neighbor Hamiltonians, basically what happens is that these currents are only going between scales. If you're at scale 1, then information is flowing to scale L+1 and L-1. And then I will also need the total current on a given scale is just what I get if I sum over all sides on a given scale. And of course that also has some total information current, which is just the time derivative of this information here. Okay, so now I'm gonna use this to explore thermalization dynamics, and I start with this. Let's see, was there any? Okay, I can't see the chat. I see there's something in the chat. Okay, sorry. Okay, so I'm plotting here now. I'm taking this transverse field Ising model, and I'm taking initial state, which is just a thermal state, or this mixed state at every side. It's 2/3 probability of spin up and 1/3 probability of spin down. And now I'm plotting here the information on scale L as a function of time. As a function of scale for different times. So at small times, most of the information is at small scales. But as time increases, you see that there is this flow of information to larger and larger scales. So there's this hump here that's moving towards larger scales, and that's just telling us, and you see that also here, that there's some information that's flowing to larger and larger scales. And this is what we expect to happen in thermalization dynamics, that there is entanglement that's generated on more and more larger and larger scales. But at the same time, there is some information that's left behind at small scales. And this is the information that we need to keep track of in order to capture local observables. And you see this here in this color plot, that there's some information that stays at all times, while there's also some information that flows to larger scales. Okay, and this is now just plotting the information current. Current is largest at small scales at short times, and then the current is peaked at larger scales at later times. But also importantly, the current goes to 0 at the smaller scales, which means that this peak, I mean, it's equivalent to saying that this peak is stuck there. It's not going to move any longer. Okay, so we can then capture the information here at this point in what we call a L local Gibbs state, which is just some Gibbs state which is a state obtained from local information only up to some scale L that captures exactly this information here. Okay. And here is a second example where we initialize the same Hamiltonian, same parameters, but the initial state is different. It's identity on every side except for one side. So the first example was a global quench. This is now a local quench where we fix the spin to be up just on a single side. And then again we see that there is this peak that's moving towards larger scales. But at the same time, there's no information. The information at small scales is also dissipating, but it's doing so in a way where there is a tail that is developing here at smaller scales. And so if I look at the information current at some particular scale here, so that's what I'm plotting here. It's the current as a function of scale. I see that the current is approaching kind of a constant at larger scales. So that's what happens in this particular case. So this was the first part where we have kind of defined this information lattice, and we've analyzed dynamics in terms of the information lattice. And now I want to use kind of the details that we get from here to try to see whether we can come up with a way of approximating the dynamics at some scale. Now first, a quick note on why does this depend on the scale at L+1? Well, if I just look at the Heisenberg time evolution of a reduced density matrix, it's just the commutator of the full density matrix and the Hamiltonian traced over all sides which are not contained in this region that I'm interested in. And there will be two types of terms in this thing. There will be terms where the Hamiltonian acts on the region of interest, and that will just generate, that will depend on the information that we already have. But there will also be Hamiltonian terms that couple the region of interest to the outside, and if the Hamiltonian is nearest neighbor, then this requires the information on L plus one side. So that's why the time derivative depends on the local information on one side further. So now the question is, can I replace this phi, which depends on L plus 1, by some psi which only depends on L? And we want to do this first by making sure that this psi is compatible with the information that we have, such that all local observables remain conserved at all times. Or rather, to ensure that the time evolution of local observables is exact. So compatibility means that there exists some density matrix at, or local information at L plus 1, which is such that it gives us the correct, such that the right hand side here is given by what we would get here if that was the correct density matrix, but it's an approximate one, so this is where the approximation comes in. But it's such that if I trace out one side so that I get the L scale L local information, then this is the same as in the initial state, or in the state that we had here. So it gets the L local information correct, but it approximates the time derivative here. Okay, now if we have the case where there is a finite thermalization time, then we know that we can just use the Gibbs form of the state for the L plus 1 state.
It's 3 minutes, sorry.
3 minutes?
3 minutes.
Okay. And then, so that's here, and then the time evolution here is just the composition of this Gibbs mapping, which maps the L local information into the L plus 1 to the time evolution here. Now in the second case, where we had infinite thermalization times a long time, so we had this current remaining, then we need to put some boundary condition at some scale. And basically what one can see from here is that since the current is becoming a constant as a function of scale, the boundary condition that we can put in is just to say, well, let's just make the current from scale L to L plus 1 to be roughly equal to the current from scale L minus 1 to L. So that gives some condition on the local information and the currents. That's not completely enough to fix everything here, but we put this constraint and plus minimizing total information, and that gives now the right hand side derivative. And if we do this, we can see that we can get diffusion constants, for example, with very high accuracy. Here's how it depends on scale, and we can get down to less than 1% variation here. Okay, and we can also look at spin expectation values on central sites, and we can get the diffusive tail for up to long times. So this works pretty well. So just to summarize, there were two parts to what I discussed. It's just the first part is a way of quantifying information flow in quantum many-body dynamics. And there we could see that at least in these Ising chains and thermalizing dynamics, which says that at long times we get a constant flow of current, information current between scales, but of course the information is flowing to large scales. And if I don't want to keep track of the entanglement or the information that's at very large scales, I need some boundary condition at some scale, and that allows us to introduce time evolution which is efficient, But now the boundary condition that we have here is equal current boundary at some scale L, and this is kind of similar to Franck's dissipator at scale L star, except that now this is in the states instead of the operators. And I think with that I'm out of time, so thank you.